Cool. Welcome back. I think last time we were taking a look at the reading, like convection, conduction through a fin in the reading. In the homework, it's a similar problem, but now we have like a base temperature and a heat sink temperature. And then in between, there's also like convection happening along the way. So this one, like if we're trying to set up like a finite difference equation, I find it always helps to like just label the points where I want temperature to be solved for. So here, if I start down here and call this like T0, and then we'll do like a T1, a T2, 3, 4, and 5. Yeah, let's do 5 and then 6 like that. So this is going to be my T1, T2, T3, T4, T5, and T6. So in this case, one of the reasons that I label this is it helps me also understand like what are the things that I already know about this problem, because I know that T0 is 100 degrees. So I don't need to solve for that. And I know that T6 is 25 degrees. So I don't need to solve for T6. So anytime those are coming up in the equation, I have real values for those that I can substitute in. So let's look at the rest of the equations based on this finite difference. So I'm taking a differential equation, turning it into finite difference equation, and yeah, and that's where I'll go from there. So at I equals 1, which is the first temperature I'm looking for, I have T0 minus 2T1 plus T2 plus delta x squared times h prime, T infinity minus delta x squared h prime times T1 equals 0. So I can rearrange this and put that T0 temperature over on the left-hand side. I can put T infinity over on the left-hand side. And I can add this thing to that T1. And then minus T0, and then this T, that's going to be a negative 2 plus h prime delta x squared times that. At I equals 2, I have T1 minus 2T2 plus T3 . And really, let's start adding things together here. Oops, sorry about that. Start recognizing the patterns, right? Times T2 plus T3 equals negative T infinity h prime times delta x squared. At I equals 3, I have T2 minus 2 plus h prime delta x squared, T3 plus T4 equals negative T infinity h prime delta x squared. I have t3 minus 2 plus h prime delta x squared t4 plus t5, it's all equal to negative t infinity h prime delta x squared. I equals 5 t4 minus 2 plus h prime delta x squared t5 plus t6 equals negative t infinity h prime delta x squared. I already know what t6 is, so I don't want it to be here. I want to put it over here. So at the first boundary condition, up at the first equation, I had that minus t0 on the right hand side. On this last one, I have this minus t6, because I already, or I can call them t base and t sync, right? T base, t sync. Because that's the main thing, that if the fin is attached there and it's in steady state, then there can't be a temperature difference between T6 and the heat sink. Same thing at the base, that they've got to be the same temperature. And these are the 5 equations that I'm trying to solve to figure out what are the temperatures throughout the fin. And let's take all of this and kind of shrink it down a little bit. Rotate it, because I've been writing at an angle. I don't know why, it just happened. And the reason I'm doing that, keeps popping up, is I want to create equation 1, equation 2, equation 3, equation 4, equation 5 for T1, T2, T3, T4, and T5. So setting up a 5 by 5 matrix with all of those coefficients. So in the first one, I've got that. And you know, I can get rid of a lot of these negative signs. 2 plus h delta x squared, and then a negative 1 here, then 0, 0, 0, because T3, 4, and 5 don't directly affect temperature 1 and 2. This is all because it's first derivative, because we just have that like second derivative. It's kind of like nearest neighbors are the things affecting the second derivative, second and first derivative. All right, so then I equals 2. I've got a negative 1, a 2 plus h delta x squared, and then a negative 1, and then a 0 and a 0, and then a 0, negative 1, 2 plus h delta x squared, then a negative 1, and 0. In equation 4, I've got a 0, a negative 1, 2 plus h delta x squared, and then a negative 1. And then in the last equation, 0, 0, 0, negative 1, 2 plus h delta x squared. And all that is going to be multiplied by this vector of my unknown T1 through T5. And the right-hand side equation is going to be that T infinity times h prime delta x squared plus, I think it's plus that, yeah, plus T base in that first equation, and then T infinity h prime delta x squared plus 0, T infinity h prime delta x squared, T infinity h prime delta x squared, T infinity h prime delta x squared plus T sync. And I know it seems like a lot, like when you're first looking at kind of finite difference methods, it seems like, why am I going through all this trouble to set up all of these equations? Why don't I just go through the calculus and just solve the ODEs myself? And you can do that. You could just solve the equation and get an answer. But the nice part about doing it this way is that now I always have a pattern. Like this left-hand side matrix, this A, it's the same pattern. Like it's a tridiagonal matrix, and there's going to be negative ones along those two off diagonals, and then that 2 plus h delta x squared is going to be along that diagonal the whole time. And then the right-hand side is going to be the same values, and the only differences are those first and last terms. So let's take a look at how we can code that in and actually get some use out of this. So I want to shrink that down, bring it over there, and shrink this down, bring it over here. So my left-hand side is going to be, I'm just going to make like, and we'll start off with n equals 5. And then if I have 5, 1, 2, 3, 4, 5, 6. So if I have 5 nodes that I'm solving for, dx is going to be L over n plus 1, like that. And L is 60 millimeters. Can I just do 60 like that? I'll do 0.06. And then HK R. What is R? That. I'm just getting all my 2H over KR. And then H, I think that was 100 watt per meter. K was 200 watt per meter Kelvin. And 1 millimeter radius fin, so R 001, like that. All right, so now I've got my like ones vector, and I can say my right-hand side A is going to be diag of ones, and it's 2 plus h prime times dx squared times that minus np dot diag of ones, just 1 less 1, minus np dot, I forgot this one, minus np dot diag of ones, 1 less, and then negative 1 there. Let's take a look at what A looks like so far. It's about what we would expect from the matrix that I had set up over here, like 2 plus something times delta x squared. Delta x is like 0.05, yeah, 0.0 or 0.005, and then that h prime is going to be right around 2. So my left-hand side matrix is all good. And then my right hand side is going to be actually, I can just use ones again, times t infinity times h prime times dx squared. And let's plug in that t infinity. What is it? Is 20 degrees. And T0 is 100. TL is 25. So my right-hand side, my first right-hand side equation, I need to add to that T0 value, so the temperature of the base, and my last one, I need to add to that the value of the fin, that TL over there. So now when I look at that right-hand side, there's two, most of them are 2, but then there's 102 and then 25 plus 2. So again, kind of makes sense from what we're doing. And I set it up this way, like using diag and n and this 0 and -1, so that if I change this from a 5 to a 50, now my right-hand side has 50 different values. Most of them are the same except for that first and last one. But let's change that back to 5 for now. So temperature, let's call it Tx, is going to be linalg.solve of A and right-hand side. And what I can see here is that when I solve this, none of the temperatures are 100 and none of them are 25 because I'm solving for all the other temperatures that are in between. And if I make dx really small, then those temperatures will get closer and closer to 125. But I shouldn't see those boundary conditions in this main like Tx solution. So it makes sense that the left-hand side is not 100 because 100 is happening at x equals 0, not x equals 0.01. So let's try bumping that up. We'll try getting more values. Change this up to 50, so our steps are even smaller. And now we start seeing, as we get closer and closer to x equals 0, we see that it's closer and closer to 100. So the boundary condition is being satisfied on both sides. 30. So the fin starts at 100 degrees, it drops some kind of like complicated exponential sort of function, and then ends up hitting that, or I guess it's like sinh and cosh sort of function, but then it does end up at that 25 degrees. Cool. And if we want to see the boundary conditions, we could always like
so would that be just increasing the number of steps almost?
Yeah. As you keep increasing the steps, the distance that you step away from the boundary condition is smaller and smaller.
Yeah.
But we can also like have the boundary conditions. Well, I mean, we could just plot them, right? We could say at 0, make a 100, and that's going to be a circle. And then we could say at 0.06, that's going to be 25, and that'll also be a circle. So we'll make this like a red circle and a blue circle. If we want to plot those 2 points on there, saying like, here's my heat source and here's my heat sink. And that way, even if we have less, even when we do like just the 5 data points, we can still see it's approximating that curve pretty well to go from heat source to heat sink. Yeah. Because those temperatures, they're not part of my like TX solution because they were already known. So it's not so much that I'm approximating them, it's that they're already exact. I already know exactly what they should be.
Then I guess my question is, if it's approximating, this is left from the heat sink.
Yeah.
Why is it still a gap? Why is it just approximating what's left until 100? That makes sense.
So when we're doing finite difference, we're not solving for like a function. Like in differential equations and in a lot of math heavy stuff, you're looking for an exact function that represents a solution. But in this case, we're saying I don't care what the function is. I just want to know what is the temperature at 10 millimeters, 20 millimeters, 30, 40, and 50. So there is no, like there is nothing to say that at 5 millimeters that it's something else. Unless I say, all right, now split it up into 5 millimeter increments. Now I get a solution at 5 millimeters. So you end up with like a bag of temperatures more so than like a function that you can approximate. You can, like, because we have discrete points, we can interpolate between them. So we could, like, if I wanted, I could go from here to here and do a linear interpolation, or use like, or use like 3 data points and assume that it's some kind of quadratic and interpolate that way. But
in this case, I guess we don't need it.
Yeah, it just depends on what we're trying to do. Yeah. Like if we need the temperature at exactly 30 millimeters, we already got that, like the halfway point. If we want to know like what's the highest heat flux, well, it's probably right there at the boundary condition. So we would probably need like more data points up here where the slope is the highest, and figure it out that way. I'm just grabbing. Should we try some encastre beam, so like fixed, clamped and clamped beam solution? Do some more while we're on a roll of finite difference. And then let's get in here, come down to this one. This one up here. All right, so encastre is a fancy way of saying that we're going to clamp the beam on both sides. So it's like a cantilever beam, but cantilevered on both sides. And then we'll apply like a continuous, like constant force across the whole thing. And the main thing that changes how the beam deflects are the boundary conditions. So I know that at 0, when x equals 0, deflection has to be 0. And when at the other side, when x equals L, W also has to be 0. And then the other thing that makes it clamped is that the slope is 0 on both sides. So there's some kind of moment that's created so that it can't, so there is no derivative there. There might be a second derivative, but there's some kind of moment making sure that it doesn't bend that way. So as I take this thing, we'll do the same thing. Well, actually, let's do this. Two, 3, 4, 5, 6. I like 6 better. 1, 2, 3, 4, 5. 1, 0, 1, 2, 3, 4, 5, 6. All right, so what I'm trying to do is figure out how far does each one of these deflect down. That's my boundary condition there. That's my boundary condition here. So I have the W0, W1, W2, W3, W4, W5, W6. So 6 different deflections, but some of them I already know. W0 equals W6 equals 0. And then I also know that W prime 0 equals W negative 1 minus W1 over 2 delta x. And that's equal to 0. So if I see a -1, it's equal to W1. W6 prime equals W7 minus W5 all over 2 delta x, which is 0. So W7, if I see that, it is a W5. So then let's start plugging in for the terms where I want to know the answer. The first place that I'm trying to solve for W is at I equals 1. And this is going to be W3 minus 4W2 plus 6W1 minus 4W0 plus W -1. And all that is equal to QH to the 4 over EI. W1 is W -1 is W1. So that W -1 turns this into a 7. And this W0 is 0. So that one goes away. When I equals 2, I have W4 minus 4W3 plus 6W2 minus 4W1 plus W0 is QH to the 4 over EI. But again, W0 is 0, so I can get rid of it. And W1 I'm trying to solve for. I equals 3 is W5 minus 4W4 plus 6W3 minus 4W2 plus W1 QH to the 4 over EI. I equals 4 is now W6 minus 4W4 plus 6W, that should be a 5, 4 minus 4W3 plus W2 QH to the 4 over EI. And then the last one is at 5. Oh, and W6 is 0. So I can get rid of that one because I'm not trying to solve for it. Now I have a W7 minus 4W6 plus 6W5 minus 4W4 plus W3. It's all QH to the 4 over EI. Last equation that we need. So W6 goes away. That one's nice. Next one, 0. And then the W7 is W5. So we end up with a 7W5 there. Cool. Now we're just trying to take those 5 equations, turn it into a 5x5 matrix. And we already know the right-hand side is all that QH to the 4 over EI terms. So my left-hand side, it's going to start off with a 7, then a -4, then a +1. So here's W1, W2, W3, W4, and W5 terms. So a 0 and 0. And then the next one, I end up with a -4W1, +6W2, -4, then a +1, 0. And we're starting to see a pattern here. A 1, -4, 6, and -4, a 1. And then a 0 for that I equals 4, a 1W2, -4, +6, then a -4, and then down in this last equation, a few zeros in here, but then a 1, a -4, and then 7, all times that W1, W2, W3, W4, W5, like that. So the main thing that changes for this like fixed beam is that the first 6 and the last 6 along that diagonal turn into a 7. So we have to add 1 to that first and last term. So let's see how that looks and see if it actually gives us what we're trying to get. Homework 5. L equals 1. E equals 200 E9. I equals 0.01 to the 4th over 12. Q is 100. N is 5. Dx is L over N plus 1. 1, 2, 3, 4, 5, 6. Yep. So if we're solving for 5 nodes, then we end up with 6 like segments that we're taking finite differences over. And I think that's all the values we need. So A is going to be and to start off, I'm just going to set the whole middle diagonal as 6. And now I'm adding, we gotta add this stuff. And if I look at A just using those diagonal commands, then I get 6s along the diagonal, -4s, and then 1s along those other diagonal parts. So I just want to change that first one. Add 1 to it, and the last one. Now I have 7, 6, 6, 6, 6, 7, 7, 6, 6, 6, 7. There we go. Cool. My right-hand side is going to be same 1s, that 1s vector that I just made up here, times Q times dx squared over E over I. Then I'm just going to go from 1 to, going to start at dx and go all the way to L minus dx. And look at the shape. Right now it's kind of tough to tell because there's only a few parts here. I can't really see that the slope is 0 over at the ends. I could add that same thing, add the boundary conditions in there. 0 and 0, 1 and 0. Say like those are the fixed ends. Again, I can't really see that the slope is 0 there. Yeah, and better is adding like more points. Let's look at how it converges. So right now, if we start off with 10 segments, it'd be like 9 points. Starting to see something. And then if we look at 19, now we're really starting to see like an encastré beam, and then go all the way up to like 39, so like 40 segments. Now we really have like a converged solution for that encastré beam. Works. More like a Gauss, yeah. Yeah, it's almost like a Gauss. For static beams, it's always like fourth derivative polynomials. Where like this Q0 is Q over EI. This one, D is 0 in this case, and I think C, no, does C be? It's not symmetric. But we could always compare to like that exact solution too. Yep. Add another page, paste this in here. So I know W of 0 equals 0, which means D is 0. W prime of 0 equals 0, which means C is 0. So now at WL, I know that 0 equals Q over EI, because Q0 is Q over EI, like that, times L to the 4th over 24 plus AL cubed over 6 plus BL squared over 2, and then 0 equals Q over EI L cubed over 6 plus AL squared over 2 plus BL is all equal to 0. And here, this is actually setting up a linear algebra problem too, where we have A and B, and left-hand side, right-hand side. So I could set it up in the same way. I could say L cubed over 6, L squared over 2, L squared over 2, and L all times A and B is equal to L to the 4 over 24, L cubed over 6 times Q over EI. And now I've got a linear algebra problem to solve my like exact integration kind of problem based on those boundary conditions. Let me bring this one over here. And we're running out of time, but well, we ran out of time. Thanks for joining. Thanks, you too.
I just saw that you posted the participation.
Yeah. I think I made a mistake somewhere in here. I'll have to go back and figure that out. Okay, thanks for joining.